Guys, so we just went through and discussed what they had complications with back in the day with ion chromatography. And quite honestly, it's everything that we would use chromatography for today. So we know that these problems had to be fixed at some point in time. But we need that lead-up process to really understand what was going on and what led to the rollout of the piece of equipment that we use in our laboratory. So all of these were problems again. And what they found is that they could separate the cations or the anions from each other as long as they had different charges. But if you started working in the same groups, then things became very complicated. And Dow once again said simple process. We do not want crazy things that have to happen in order to train people to use this technology or process in the laboratory. We want it simple. All right. So Dow was still kind of leading this whole charge. And all of their scientists, including Hamish Small, again, was working on better and better and better resins. There was a point at which these resins became maybe plausible. They had possibility. They had hope. And those resins were able to take some of those problems in the past, and they could separate, finally, these charges from each other. It required different stationary phases, and we'll talk about some of these stationary phases in a little bit, but the stationary phases really played a larger role in making a better resin. Just when they think that they are on the brink of finding something, we're improving our resin even more. We're going to be able to separate all of our negative ones or our positive ones from each other. What they discovered is that that wasn't the only problem. Another problem was detection. How would you detect them? There was an issue. Detection was a problem with these people. You know, up until this point, detection very often, like UV vis technology, detection was pretty simple because they could absorb light. And that's really what they played off of a lot of times. Putting a UV vis detector at the end of an instrument, that was pretty common back in the day. We could absorb some light. If it was a colored solution, it would absorb visible. Some of the organic molecules would absorb the UV light, so that wasn't an issue at all. But, these were cations and anions. They really weren't absorbing any kind of light. So they needed to change the detector up on the other end. Just when they thought that they had a better resin that could possibly separate all of the negatives and the positives and stuff from each other, their problem then began on the other end, the detection side. So what's universal that all cations and anions have in common? And that's conductivity, right? They all carry some type of charge. And if we have a conductivity detector on the end, then we could pick up some of those charges and we could call it a positive signal. So conductivity is universal. That's what it was going good about it. The problem is that the eluents, the mobile phases, that's what we would call these today, the mobile phases also had charges. Right? They were taking salt solutions and they were dissolving salt solutions into some water. And water and salt is going to create some electrolytes, and those electrolytes are going to be pumped through the system. And as they pump through the system, they're going to go through the detector, and those are going to carry some charge. No way around it. So they thought they were at a stopping point. What on earth do we do? Conductivity would be great. Conductivity is universal. Conductivity measures all of these ions that are coming through that we want to separate. But the problem is that the liquids that we're pushing these things through with are also charges, and they're also going to be picking up a signal because conductivity is so universal. That was the drawback. That was the biggest drawback of conductivity. So what these people were seeing is that as the mobile phase was coming through, it would create some noise. I mean, that's some charges that it's coming through, and that conductivity is picking those up. And then every now and then something from the sample would come in, and it would kind of come in and mix in with the stuff too. But, if I didn't draw this a different color and I just lifted it green, you might think it was part of the noise that was coming from the background. So that was an issue that they had to figure out how to deal with it. Conductivity was not going to work, people. And the reason that conductivity was not going to work is because it carried charges. So then they said, okay, well, what if we just do away with the salts that we are putting into the water? These eluents and the mobile phases that we're using, why not just use water and that's it? Distilled, deionized water. That could probably hamper the noise that we're getting from the instrument. And they thought this thing would work, right? Yeah. It's just water. It's pure water. As it's coming through, we're going to get a pretty clean baseline. It's not going to be an issue. We've just solved a problem. Well, here's the problem with that story. As the things were traveling through this resin or the column and out the other end, if they just used water as the mobile phase, the water wasn't doing anything to retard the ions, to hold them back. There was nothing there that water was going for it. Especially on small scale. Again, this is Dow Chemical. Huge industry. Big scales of stuff that's going on. Water would work at the big scale. We're talking like huge columns bigger than people. Right? Liters and liters and liters and liters of mobile phase going through. Pretty large samples that are going through the column. What they were finding is that water was working out okay because it was huge columns with tons of stationary phase. But when we get to small scale, the small scale stuff was small scale, meaning there's not a lot of time, not a lot of room, not a lot of space to do the separation in. And it just wasn't quite working out well for them. They could not get species to come out at different retention times. Too tiny. Not enough time. Unless you want to make these columns like super huge and super long, which is not practical, they're not going to work. So water worked great in large scale systems, but not in small ones. And they figured out that stationary phase might be a problem. We worked so long on these resins, and we got so close. And now the problem is with the stupid mobile phases that we're pushing through. And we didn't think about it. Nothing that we were using that did not have a charge was able to push things through at different retention times and hold things back. So if this is the setup that we have to have, and that's kind of what Dow wanted them to do, keep it aqueous. We wanted to keep it aqueous. Then we're going to have to go back to the drawing board and we're going to have to take a look at these stationary phases again. And for the next 10 to 15 years, they worked on stationary phase after stationary phase after stationary phase. It's kind of sad. 10, 15 years in the making, we still really don't have a proper resin. So there's a certain point now. Remember, this started kind of in the 1950s. So this is leading us into the 1970s now. And after this time, the group of scientists that were working together became scattered. So all of the core people that was working on this technology for Dow began to quit the company, move off, take jobs somewhere else. Maybe they were still with Dow, but they were just in a different location, in a different area, in a different research lab, except for Hamish. Hamish Small was still worried about the resins, about the detectors, about ion exchange. And after this time, what he decided is that another viewpoint was needed. You reckon? I would say so. 10 to 15 years, I would say another viewpoint is probably pretty important. And he said, listen, we've been looking at this all wrong. Maybe the problem isn't with the resins. We've been working on them all this time. We thought we found one that worked. The issue, though, is that we were using water as a mobile phase. And those two, hand in hand, did not get along very well. We couldn't get any retardation factor, any retention time differences. And we can't use mobile phases that have salts or powders dissolved up in them because they create ions and they come through the system. But what if we place something that's in between the outlet of the column and the detector? There's the detector. Here's the end of the column. What if we place something right here that could maybe suppress the signal that we're getting from the mobile phases? If we do that, then the whole problem of the noise from the mobile phase could be dampened. And we would get maybe slight variation instead of a noisy background. And this piece could be the key. If we could suppress the signal from the mobile phase, then we could go back to the drawing board and pull out what we were doing 10 years ago and use water with a little bit of buffer in the mobile phases, use the resins that we know worked, and we could possibly get different retention times because we now have a system that gets along just fine. 10 years, 15 years, they decided maybe the problem isn't the mobile phase. Maybe the problem isn't the stationary phase. But maybe they need to add something else to the mix to make this a little bit better. So in 1971, that is when the very first piece was introduced to do this job. And this piece was called a stripper. Well, I guess people didn't like the word stripper, especially drunken chemists that work on the weekends. So they decided to get rid of this word. Let's not use the word stripper. Let's use the word suppressor. Now people will probably argue about the word suppressor. But that's okay. That's what we call it today. And what happens is that the mobile phase will pass through the suppressor. And the suppressor's job is to remove the signal from the mobile phase. And what we end up with in the end is basically something like water. So we start off with a buffered water system. It goes through the suppressor. The suppressor takes out the buffers or the salts that might interfere with the baseline, and then we just spit water out that will eventually lead to the detector. And they said, you know what, Hamish, this is good. I think you're onto something now. We should have thought about this years and years and years ago. But if this is what happens, if we can utilize the buffer system in the beginning and then allow it to retain compounds and give us different retention times, and then in the end result, we just end up with water that doesn't interfere with our detector, then we have just fixed our problem. After all of this time, we should have thought this about a little bit sooner, right? Well, it kind of worked. But here's the other problem. The suppressor that was used on the system, there was a limit to it. You could only put in so much, people, before it got overloaded. And now we're back to the drawing board. Because Dow was like, listen, this still doesn't make sense. No one in their right mind is going to go through and constantly change these suppressors out. Because if you're telling us that it does its job and it works and it does what it's supposed to do, but it's only going to do it for a limited amount of time, no one is going to have a cabinet full of suppressors that they can just pull from and change midway through or at the end of so many number of runs and just waste money. It is not fiscally plausible to do that, and it doesn't make sense. So Hamish said, okay, well, it's got to be cleaned. Maybe they can order a few. Maybe we can take the suppressor and maybe we can clean the suppressor. And if we clean the suppressor, we can reuse it. And that's a great idea too, but the problem is that this takes time. You have to make sure that someone is cleaning it the right way. You have to make sure that you're cleaning it for a long enough time period. You have to make sure that everything is flushed out of the system. You have to make sure that everything is fully gone. And that way, when you put it back on, you know it's going to work for you. Do you really want to invest money into an employee, and that's really all that they're doing, is regenerating and cleaning the suppressor so it can be reused? And Dow said, probably not. That's not going to make any sense either. No one's going to bring on an extra set of hands just to keep these suppressors cleaned so other people can continue to run sample after sample after sample after sample. So the replacement was a problem. They thought that no one would go for this at all, period. No one's going to have a buy-in. And if no one's going to have a buy-in, then what's the point in mass producing it or trying to sell it to somebody? Again, doesn't make sense. So Hamish Small went back and said, okay, fine. The suppressor was a good idea. This suppressor makes sense in the short term, but it doesn't make sense in long term. So he went back to the stationary phases. And he said, let's try to figure out if we can maybe pull out some new stationary phases that would able to do the job a little bit better. And throughout the 10, 15 years, Hamish went back and took a look at all of the different versions that they were making and different versions that they were using, and he saw something in particular that caught his eye. And this was a stationary phase that used what we called a sulfonated matrix. Sulfonate group is basically your H2SO4 group or your SO4 group. That's your sulfonate group. The sulfonate group allowed the matrix to be water soluble. All right? So remember, they said that this should stay aqueous. It should be able to house stationary phases and samples that are aqueous in nature. You can't have something that's hydrophobic. It's not going to work. So this sulfonated matrix helped improve the water solubility, or the water-loving characteristic of this species that it's at play. This sulfonated matrix, at that particular time in Dow, it was called a gel-liquid stationary phase, or a gel-liquid extraction. And what they decided to use during this time was a polystyrene that was cross-linked together. So I'm going to put cross-link here in the very beginning. Cross-linked polystyrene. What I want you to think of is a piece of lattice that you might see on a front porch or something. All right? So here are my stationary phases, or my stationary phase. And here are some polystyrene particles that might be in the stationary phase. These things kind of hook up, and they cross-link. That's what we call them. And they cross-link, and they are very ordered, and they are very structured, and this is kind of its shape that it begins to take on. It's kind of like a piece of lattice. All right, so these cross-linked polystyrene was a very good step. The problem is that polystyrene, well, that's an organic molecule. All right, styrene is pretty much a benzene ring with a carbon that's double bonded to another carbon that's coming out here off to the side. This is very organic-y. It doesn't like water. Styrene is not water soluble. All right, well, we got to keep it in water. That's what Dow wanted. So what these people decided to do when they were playing around with the resins is, let's just slap some sulfonates on it. SO4, 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 SO4. Let's just put them everywhere. If you've taken organic chemistry, you kind of understand how this process would happen. Here we've got a benzene molecule, and that benzene molecule needs to be sulfonated. So benzene has reactivity. There are active sites and deactive sites on a benzene ring, which we can kind of relate to the word activator and deactivator if you've talked about that in organic so far. Well, we can sulfonate a benzene ring pretty easy. The only thing that we have to do is add a little bit of H2SO4 and H2SO4. That's basically saying flood the system with sulfuric acid, because sulfuric acid will protonate, create some charge distribution, and that SO4 can then go in for attack on the benzene ring. So we disturb the benzene a little bit. Sulfonate, SO4, goes on to the benzene ring, and then all of a sudden we have a sulfonated styrene molecule. And that improved the water solubility of what goes on the inside. So again, polystyrene is not hydrophilic. That means water-loving. Polystyrene is hydrophobic. If you want to stay water, you got to give something that water can go into and not be afraid of, and styrene's not going to cut it. But the sulfonation of the styrene helped improve this resin that was taking place at the time. All right, so now, finally, still in 1971, but now we're looking at November of 1971. This new material, actually it was kind of old, right? This sulfonated resin. So I'm going to put sulfonated polystyrene, PS, and a suppressor, and 100 microliters of a standard was injected onto a column. This standard had a couple of different components. It was sodium plus 1, and it was potassium plus 1, and it was lithium plus 1. Remember, these were the problems. They could separate positive 2s and positive 1s, negative 1s and negative 2s, but when it was the same family, they couldn't. They had a more difficult time to do it. Well, Hamish Small put all of these new pieces that were kind of regurgitated and rehashed together, and he ran it. And he waited for the chromatogram to come off of the instrument. During that time, very little computer work, more integrator type of stuff, more strip pins, strip chart recorders. But it was a very similar picture of what we would kind of associate with as far as a chromatogram goes today. And this is the picture of his laboratory notebook. This is the actual thing that was attached to his lab notebook when he worked in Dow Chemical. And this is a picture and a representation of the first successful separation of your alkali metals. Your lithium, as you can see, is in the front, and then your sodium comes next, and then your potassium comes third. They're all positive ones. They all show peaks, and they all separated. So Hamish was finally to say, Eureka. I think I done it. Now, I know, Dow, you're going to frown on my suppressor, but this proves that it works. If we can figure out a better suppressor or a better way to make it or a better way to use it, then we have a system that's going for us. And we can take these things now and we can separate them one by one. We can use buffered solutions as mobile phases. We get different retention times. I rehashed your sulfonated polystyrene resins that we had worked on 10 or 15 years ago. I put them back into a column. I made a standard, and this proves that we can separate those pieces. There you go. And Dow said, congratulations. This is a step in the right direction, Hamish. It looks like you've done your job. It looks like you've done what we wanted you to do. But there's a problem. We're sorry, Hamish, but this is not going to work. This is not practical. And he said, no, I know the suppressor needs work. I know that we need to do something with the suppressor, but if we can figure that out, then we've got a practical model here that's going to be very easy to be used by anyone. And they said, no, that's not what we're talking about. What we're talking about here are your retention times. This is not practical for a laboratory because no one will go for these retention times. So I don't know what you were thinking. It's a step in the right direction, but you need to go back to the drawing board and you need to reattempt this and rework it a little bit because this is not going to fly with our people. And Hamish said, well, what do you mean? It's not going to work. I'm showing you that it does. He's, no. Practicality, Hamish. Practicality. Because your lithium that came off first took 63 minutes. The sodium that you ran took 82 minutes. And the potassium that you ran, that took 134 minutes, Hamish. So good step in the right direction. You were able to separate them, but we need better than this. Because no one is going to run one sample, for 2 hours just to get the values of potassium. Could you imagine if you had 100 samples to run? There's no way. You'd be there for weeks. No way. And that stops at potassium. What happens if you go lower than potassium on the table? What happens when you go to the +2s? Those are going to stay in there a little bit longer because they're +2s. We know that. We've already seen that. We've discovered that already. So what's going to happen when you venture outside of these simple little 3 cations? You're talking hours of runtime per sample. go back to the drawing board, try to do something a little bit better and something that makes a little bit more sense. So Hamish packs it up and he goes back to the lab and he begins to tinker and play around with more things to try to make this a little bit better.